Hello and welcome to today's lecture. So before I begin my discussion of the plan is to talk about orientations. Before I do that, let me just give one more example of some special classes of differential forms. So this is differential forms on Lie groups. Whenever we're in the setting of Lie groups, it's natural to look at whatever object we are considering. It's natural to consider objects which are preserved by the left translations, or for that matter right translations as well. So let's say we make the following definition: omega and omega km is left invariant then we say that omega if, well, so I have this, the left translation diffeomorphism, if, and the pullback of Lg star of omega at the identity, well, not quite identity. So let's recall that Lg is going from G to G. So therefore the derivative of Lg dLg at identity is going from the tangent space here to tangent space here. And if I put then if I look at the corresponding map on alternating K tensors, that map, so this is what we have been calling Lg star, upper star. So sorry, not this one. The next one is what we have been calling Lg upper star. So the corresponding map will be from the alternating K tensors on this to this, which is a star of this map, which is what we have been calling Lg star at well, you can say at identity. Let me just leave it like that. So this here I should change it to G equal to omega E. And so as this is more or less the same way we define left invariant vector fields, except that the maps, the induced map corresponding to left translation goes in the opposite direction. Even though I have identity as a base reference point here, just like for left invariant vector fields, one can check that this is equivalent to saying that Lg star of omega Gp equal to omega p for all, oh, by the way, here I should say for all G in G, and here for all G in G, and for all P in G as well. So P goes to GP under left translation, so the corresponding map on K forms will be in the opposite, go in the opposite direction, and it will give me this. And so this is one thing. The second thing is that also one can check that the space of left invariant, here I say space, since the set of left invariant forms of a given degree forms a vector space, we can add them or multiply by scalar. One can check that the space of left invariant K forms is isomorphic. Well, essentially, whatever happens on the tangent space at identity should determine everything. Or for that matter, as this equation shows, whatever happens at one point should determine whatever happens on the whole group. But it's more convenient to work with the identity. So let's, space of left invariant K forms is isomorphic to AKTEG. And this isomorphism is very similar to what we did for vector fields. So if one starts with, if alpha belongs to AKTEG, or rather, if omega is left invariant, I start with a left invariant form and just map it to send it to its value at the identity. So in other words, an element of AKTEG. And this map is an isomorphism. So if I know it, and the proof is just exactly like this. And so just if you are given something, an element of AKTEG, I can obtain an omega g by putting this LG star on this side by taking the inverse. And that one can check that it's an isomorphism. But what requires a bit of proof, which I didn't prove even for vector fields, is that when we do this, if I start with something, if alpha belongs to AKTEG and omega equal to omega g equal to LG star inverse alpha, then omega is smooth. This is the thing which has to be checked. As g changes, what we get is a smooth form on the Lie group. So this part has to be checked, but again, this has to be checked even for the vector fields, which I didn't go over. As reference, I would recommend John Lee's book on smooth manifolds that has a short proof for the vector field case and this case as well. Well, there is this is one thing. The other example that I wanted to talk about is, let's look at another example. Is let omega be in the one form on the circle be omega equals minus y dx plus x dy, whatever we had been talking about in the last lecture, the same form, but except that I pull it back to S1. That form was on R2 minus the origin. Now I pulled it back to S1. So this form, and we have seen that this is closed, but not exact on R2 minus 0, and so one can prove that it's not exact on S1 as well. But what I want to look at now is the n-dimensional torus n times. So we have this projection maps pi I, and this is just pi I of x1 xi xn equal to xi. So here each xi is an element of S1. This xi does not denote Euclidean coordinates, but this Cartesian product. These xi's come from the Cartesian product. Now the point is that I have this fixed one form on S1. I can pull it back to the n-dimensional torus and get a form here. Depending on which projection I take, I get different forms. Well, using these one forms, I can, for any multi-index I equal to I1 Ik, we get a k form out of this in the usual way. Omega I is, so this I'll call omega I. Omega capital I is omega I1, omega Ik, and this will be in omega k Tn. And one can check, well, we have already proved that D of a product is, the Leibniz rule is satisfied. Therefore, one can check since all of these, moreover, the fact that omega is closed will imply that the pullback is also closed. Since we know that D and the pullback operation commute, pullback of a closed form will be closed. Therefore, I get this, omega I is closed, and I also know that wedge product of closed forms is closed by the Leibniz rule. So therefore, this is closed. So omega I is closed. Well, the significance of these forms is becomes evident in topology. So whenever we have closed forms, they have topological significance, and these specific forms, it turns out, are basically capture all the topological content of the n-dimensional torus. So now at this point, I would like to move on to a different aspect of manifolds. This is the concept of orientation. Orientations of manifolds. And I'll have to end the course after this discussion of this topic. The natural way of proceeding would have been to talk about integration on manifolds, which is where the real role of differential forms become evident. We use differential forms even for orientation, but the real significance or the real necessity becomes clear when we talk about integration. However, I will not be doing that. And once we talk about integration of forms, then theorem the big theorem would be Stokes' theorem on manifolds. There one would have to deal with manifolds with boundary and so on. But let me just talk briefly about the concept of an oriented manifold. As it, well, what one really needs to start with is just the concept of an oriented vector space. Let V be a n-dimensional vector space. Now, so let this beta be the set of all n tuples of this v1, v2, vn. Since I've used this round brackets, so this it's an ordered n tuple set of all such things such that this unordered set is a basis of V. In other words, beta is just the collection of bases of V, but we are looking at ordered bases. So formally, this is just a subset of V cross V n times. Now, in this, the set of all bases of V, we can ask when two bases are sort of have the give rise to the same notion of orientation. Now, of course, we don't have a notion of a orientation yet, but so here's what one would like to do. So given B1 equal to V1 Vn, B2 equals W1 Wn in this beta. So in other words, given two bases, we can there exist Aij in Rn, I between 1 and n, j between 1 and n with, so I can just expand V1 in terms of the W's, A11 W1 plus A1n Wn, etc. Vn is An1 W1 plus Ann Wn. If I do this, then that amounts to saying, so now let's look at this matrix A. Let A equals this matrix A11, A1n, the change of basis matrix Ann. So we say that these two bases B1 and B2 are equivalent. We write, rather than we say that, let me just say we write B1 is equivalent to B2 if determinant of this matrix is positive. So now then a small check, one can check that this notation tilde is actually an equivalence relation on beta. So in other words, reflexivity, symmetry and transitivity hold for this relation tilde. So let's look at this set of equivalence classes of this. Has exactly two elements, i.e. there are precisely two equivalence classes for tilde. And the proof is very short. So to say that there are precisely two equivalence classes for this, all I have to do is come up with two bases and such that any other basis is equivalent to one of these two. And of course, these two should not be equivalent to each other. So let me start with any basis. Let B1 equals V1 in beta, and the second basis, all I do is I just interchange V2 and V1 and keep the remaining vectors the same. V1, V2, V1, V3 onwards, they're in the same order as for B1. And of course, this is the same as a set. This is the same as this, so this is still a basis, just that the ordering has changed. First of all, B1 is not equivalent to B2. Well, if I write the change of basis matrix, I would be, so V1 would be 0 times V1, let's call this, to be consistent with our earlier notation, W1 Wn. So it's 0 times W1 plus 1 times W2 plus remaining things are all 0. And V2 would be 1 times W1 plus 0 times W2, and everything else is 0. And as for the remaining stuff, they're all, so 1 times. So for the ith term, I'll just get an I for the Wn, etc. So in other words, this matrix A will be 0, 1, 1, 0, and once elsewhere on the diagonal, and zeros off diagonal apart from these two, the first two. So det A will be just -1. And so this one, B1 and B2 are not equivalent. Now anything else is equivalent to one of these two. And the reason is let C equals, I'll take any other basis. Let me call it x1, xn in beta. Well, as usual, I can write C in terms of this. Let me start by writing C, this basis in terms of the basis B1. So A11, V1, etc. A1n, Vn, xn equal to An1, V1 plus Ann, Vn. Now, and if this, suppose if det A is positive, then C is equivalent to B1 by definition. Suppose that A is negative, then we would like to claim that, C is actually equivalent to B2. That would prove what we want, that there are exactly two equivalence classes. So this, whatever I wrote here, this expansion, let me rewrite in terms of the W's, which is a basis comprising, which makes up B2. So x1 equals, now for B2, V1 and V2 are switched. So I would have to write it like this, A12 W1 plus A11 W2, and the remaining terms are the same. So that would be A13 W3 etc. A1n Wn, and likewise x, and this will be done for all the terms. Xn is A n2 W1 plus an1 W2, and then an3 onwards it would be the same, ann Wn. In other words, the matrix, new matrix A tilde, such that which relates the basis C with the basis B, is given by just, all I've done is I've interchanged is obtained from the matrix A. All the columns are the same except the first two columns have been interchanged. Here it's A12, AN2 is the first column here. The second column is A11 all the way up to AN1, while for A it was the other way. Obtained from A by interchanging the first two columns of A. Therefore, det A tilde is equal to the negative of det A, and we already assumed that A is negative, so this is positive. So therefore, C is equivalent to B2. So that we have two equivalence classes. Each equivalence class, so that completes that. Equivalence class of tilde is called an orientation of V. So let's use the script O to denote an equivalence class. If an orientation has been chosen, then if we take any basis is said to be oriented if this B belongs to theta. So if B lies in that equivalence class which we have chosen, then we call it oriented. So the simplest example to keep in mind is example, the standard orientation O on Rn is the equivalence class containing the standard basis E1, E2, En. So in other words, we say that a basis of Rn is oriented if that basis is related to E1 up to En with the change of basis matrix having positive determinant. Right. Now, there is a very nice way of relating this concept of orientation to differential n forms on V. So, proposition. each non-zero omega in A and V, alternating n forms on V, determines an orientation on V. And let's denote this by O subscript omega. So O subscript omega is the set of all bases B equal to V1 up to Vn in beta such that omega evaluated on V1 up to Vn is positive. And if you have two different omega 1 and omega 2 in A and V non-zero forms, determine the same orientation if and only if omega 1, they're just positive multiples of each other. That's a crucial, the sign of C is the crucial thing here with C greater than 0. So in short, the choice of a n form, non-vanishing n form, will give us an orientation, and it's well, and we can say when exactly if we start with a different form, then we can say that we'll get a different orientation only if the two forms are. We know that, first of all, we know that A and V is one dimensional. So any two n forms are multiples of each other, scalar multiples. But they determine the same orientation if and only if there are positive multiples of each other. So I'll talk about this the next time, and also about how this can be used to give a couple of different characterizations of orientations on manifolds. Okay, thank you.